Hello everyone, I'm going to talk about Karchmer-Wigderson games for hazard-free computation. This is a joint work with Ikenmeyer and Balagopal Komarath. So hazards in digital logic are spurious electronic glitches or pulses that occur at an output gate during an input transition due to physical delays in wires or gates. So for example, consider the implementation of multiplexer on one bit shown here. This output gate outputs the value of y if x is set to 1, and if x is set to 0, it outputs the value of z. So consider the evaluation of the circuit at the input 0, 1, 1. At 0, 1, 1, x is set to 0, so this red AND gate evaluates to 0, whereas this black AND gate evaluates to 1, and so the overall output evaluates to 1. Now consider the transition from this input to the input 1, 1, 1. So basically, you flip the bit x. Further, suppose that this red AND gate has longer delays than this black AND gate, right? So what happens temporarily is this, when you flip the input bit x to 1, this red AND gate continues to see the old value, which is 0. And this black AND gate sees the new value, which is also 0. Why? Because x is set to 1 now, and so negation of x is 0, right? So for a moment, this output gates outputs the value 0, right? And this is known as 101 glitch, right? So you are supposed to see 1 continuously, but for a moment you will see 0. And why are hazards important in practice? Because if you have a hazard-free implementation, then you will be sure that no glitches will occur, regardless of the physical delays in wires or gates. Also, hazards are major source of power dissipation in circuits, and so they are important in VLSI design. In cybersecurity, they are used for gate-level information flow tracking, while in distributed system, hazard-free implementation is solved when agents with unsynchronized clock domains perform parallel computation. They are also studied in logic, properly known as clean logic. Right? So let's try to understand them mathematically now. So we have a function f on n bits, right? And consider a string alpha on 0, u, 1 to the n. Right? So it's an n-bit string over 0, 1, and u. And with this string, you can think of it really as a partial input, where the bits which are set to 1 and 0 are defined bits, stable bits, whereas the undefined bits can take any value between 0 and 1. With this interpretation, you can define a subcube with respect to this partial input alpha, or this is string alpha, which is basically the set of all Boolean strings which agrees with alpha I whenever alpha I is not equal to u. Right? So basically what you do is you take the alpha I, and for u, you can replace it with 0 or 1 and obtain a new string, right? So for example, if your alpha was u10u, then the subcube of this string is given by the set of these strings, right? So you can see in the place of u and u, you have replaced with all possible values of 1 and 0s, right? So you get 4 such strings, Boolean strings, right? So this is what we understand by subcube of alpha. Once we have this notion, we can define what is called as a hazard-free extension of the Boolean function f, and we denote it by f bar. So its input is a string over 0, 1, u to the n. So you will interpret this string as a subcube. And on this subcube, if the function f is constant, then you output that constant value. In particular, if f is equal to 1 everywhere, then you output 1. If f is equal to 0 everywhere on the subcube, then you output 0. And if neither of the case holds, then you output u. Okay, so this is how the hazard-free extension is defined. And for every string on which hazard-free extension evaluates to 1 is also known as one certificate of the function, or an implicant of the function f. Similarly, on every string on which a hazard-free extension f bar evaluates to 0 is known as 0 certificate or implicate of f. Right, so these are basically just a set of literals. And we also need a definition of prime implicant. A prime implicant is just an implicant which is minimal with respect to the set inclusion. That is, any subset of this set of literals is not an implicant of the function f. Right? So let us now see what do we mean by a circuit to be hazard-free. And for this, we need to extend the Boolean logic to the clean logic while incorporating the undefined bit. Right? So how do we extend the Boolean gates? So let's look at AND. So 0 and undefined or unstable, you really think of it as an undefined or unstable bit. So here we know the function value, so it should output 0. 1 and undefined, we don't know the function value. It will depend on this undefined bit. So the function value is again undefined. Undefined and undefined is undefined. Similarly, 1 or undefined is 1. 0 or undefined is undefined. Undefined or undefined is undefined. Similarly, negation of undefined is undefined. Right. So now inductively on the structure of the circuit, you can evaluate a circuit given a string in 0, 1, u to the n, right? And when you can evaluate a circuit on such a string, then you say that C computes F in a hazard-free way if on every string, the output of C agrees with the hazard-free extension, right? So really it's saying that if I input a certificate, alpha is a, say, 1 certificate or a 0 certificate, then the circuit should output 1 or 0, right? And conversely, we say that C has a hazard at alpha if C of alpha is not equal to F bar of alpha. That is, if alpha is a 1 certificate, that is F bar of alpha is 1, and C of alpha evaluates to 0. And in such a case, alpha is said to be 1 hazard. Similarly, if alpha is said to be a 0 hazard if alpha is a 0 certificate, but the circuit evaluates to undefined on this value. Right? So let's look at an example, multiplexer function over 1 bit. And we had seen this implementation before, that is x and y or negation x and z. Right? And we had seen that it has this 1, 0, 1 hazard, right? So in this mathematical terms, now it means the following. So consider the certificate U11. This is a 1 certificate because irrespective of the value of x, the function value will be 1, right? On this certificate, let's see how the circuit evaluates. So x is set to undefined and y is set to 1. So therefore, this AND gets evaluated to undefined. Now x is set to undefined, therefore negation of x is undefined, and z is set to 1. So therefore, this AND gate also evaluates to undefined. And in particular, then this implies that the output gate also evaluates to undefined. So now here is just one certificate on which the circuit evaluates to undefined, and therefore it is a 1 hazard. Right? An easy way to get rid of this hazard is by including the term y and z in the DNF representation of this mux1. Right? So in terms of prior work, as early as Huffman had looked at hazard-free circuits, and he showed that every Boolean function does have a hazard-free circuit. In particular, the one is the DNF with all minimal 1 certificates. But it can be of exponential size. Example, majority, all n by 2 size sets are minimal 1 size certificate, right? Later on, Eichelberger gave an exponential time algorithm to detect hazards and showed that hazard-free DNF must include all minimal 1 certificates. So it's sort of tightened with the Huffman part, right? Then later, Mate, Dias, and Chuang gave an algorithm to construct hazard-free DNF, given a DNF as an input. Let's put this algorithm in perspective with this bound from Chandra and Markovsky, which says that there exist functions which have nearly as many as possible prime implicants and implicates, that is at least 3 to the n over n. And also there exists DNF with k terms which have as many as 3 to the k over 3 prime implicants. Right? So the previous algorithm was necessarily an exponential time algorithm. Right? Recently, the work of Ikenmeyer, Komarath, Lenzen, Lesikov, Mokov, and Srinivasan regenerated interest in hazard-free complexity. In particular, they proved that for monotone functions F, the two complexity coincide. That is, the hazard-free complexity is equal to the monotone complexity. And more importantly, they showed that hazard-free complexity of F is lower bounded by the monotone complexity of hazard derivative of F. And this opens up new ways to prove lower bounds for hazard-free complexity by the monotone complexity. They also showed that detecting hazard is NP-hard and gave a construction for k-bit hazard-free circuits. That is, circuits which are correct on inputs in which there are at most k undefined bits. Later on, in a joint work with Komarath, we showed that the brute force algorithm to detect hazards is optimal, assuming SCTH even in low-depth circuits. For DNFs, we gave a polytime algorithm, and it remains open to characterize the complexity in depth 3 circuits. Later, Yukna proved some more structural results. Among other things, he showed that hazard-free De Morgan circuits must produce all prime implicants and prime implicates syntactically. Also, that minimal hazard-free circuit for monotone functions are in fact monotone. So the negations are useless for computing monotone functions in a hazard-free way. We also showed that every Boolean function on n bit has a hazard-free circuit of size order 2 to the n over n, so nearly matching the Lyapunov's upper bound. Right? So in essence, what we have is there is only one way to prove lower bound on hazard-free complexity of f, and that is via the monotone complexity of hazard derivative of f. So let us look at what is this hazard derivative of f. So of a Boolean function f over n bits, the hazard derivative is another Boolean function over 2n bits, where the first part of the input is denoted by x, and the second part of n bits we denoted by y. And given x and y, you construct the string x plus u dot y over 0, 1, u, which is basically the bitwise operation. So it is x1 plus u dot y1, then x2 plus u dot y2, and so on and so forth. And essentially, what it is saying is that if y1 is equal to, if yi is equal to 0, then that bit should be equal to xi. And if yi is equal to 1, then that bit should be equal to u. Right? So when you get this string, with this string, when you interpret it as a subq, now you look over the subq whether f is constant or not. If f is not constant on the subq, then you are equal to 1. And if it is equal to a constant function, then you output 0. Right? So this is the hazard derivative of a Boolean function. And Ikenmeyer et al. Showed that when you consider this hazard derivative with respect to the second set of variables, that is fix the first set of variables to an input x, and within the second set of variables y, this hazard derivative is a monotone function. And more importantly, they showed that the hazard-free complexity of f is lower bounded by the monotone complexity of the hazard derivative at any input x. So you can choose an input x of your own liking, right? And this is the way to prove lower bound on hazard-free complexity. So the question is, can we use hazard derivatives to prove optimal lower bounds? In the course of this work, we will show that the answer to this question is no. Let us look at an example. So this is the multiplexer function. So multiplexer on n bit has n address bits, and these n address bits gives an address in the next 2 to the n bits. So it is defined in total over n plus 2 to the n bits. And then you output that bit in the x, right? So you treat the first n bits as a number, and then you output that bit in x. Okay, that is the multiplexer function. Multiplexer function over 1 bit, multiplexer function over 1 bit can be implemented by this hazard-free optimal formula. We will see later that this is indeed an optimal formula, and it is similar to the one that we saw earlier, but this has 5 leaves, whereas the earlier one had 6 leaves. And there is a well-known recurrence relation for multiplexer in terms of multiplexer on 1 bit and multiplexer on n-1. So you can multiplex on the first bit s1, and depending on its value, you can output the other function, which is a multiplexer on n-1, or s1 is equal to 1, which is also another multiplexer on n-1 bit. Right? So using this recurrence, you can unfold this formula further to n levels, and you can show that this is in fact a hazard-free formula computing multiplexer function, and the size of this formula based on this recurrence is at most 2 times 3 to the n-1. Right? So can we prove that this is the optimal size, or can we improve the size upper bound? So let us look at the hazard derivative method that we know, what sort of lower bound it can prove. Right? So we claim that the hazard derivative of the multiplexer function with respect to any input s comma x is at most n times 2 to the n. So let's look at a particular input 0, 0, and at this place, this hazard derivative is a Boolean function which looks like this. So you consider the input 0 plus u dot y, which is basically saying that if yi is equal to 0, then you keep it 0. If yi is equal to 1, then you make it a u. Consider this a string. And when you consider this a string, this is a 2 to the n length string. And when you restrict it to the positions given by the subq 0 plus u dot t, right? Then this string is a not all 0 string. Then you output 1, and if it is, then you output 0. Right? So just to reiterate, you consider this a string, and this should not be equal to all zeros on the positions given by the subcube 0 plus u dot t. And this is the subcube of all Boolean strings which are less than equal to t in the Boolean partial order. Okay. And if it is if it is equal to all 0, then you output 0. Right. So really, to implement this, what you need to see is that right, there is a u in one of the positions, and that u will be there if the corresponding bit in the y is 1. Right. So you really need to check if there is a bit in y which is 1, and if such, then this bit should be covered by the subcube position. right? And so which means that this index b should be less than equal to b. That means wherever bi is 1, ti must also be equal to 1. And this is the implementation, a monotone implementation of the hazard derivative of multiplexer function at 0, 0. Clearly you can see the bound, that is, it is n plus 1 times 2 to the n. So from this we observe that hazard derivative can only prove a lower bound of n times 2 to the n on the formula size, right? Whereas we had seen that the upper bound is 2 times 3 to the n minus 1. So what is really the truth here, right? And we will show, in fact, that the upper bound is tight. So by improving the lower bound, we will in fact show that the hazard-free formula complexity of multiplexer is at least 2 times 3 to the n minus 1. To show this, we will introduce a hazard-free version of Karchmer-Wigderson game for the function f. In this game, Alice gets a 1 certificate alpha and Bob gets a 0 certificate beta. And their goal is to determine an index I in n such that alpha I is not equal to beta I, and at the same time, alpha I and beta I are not equal to u. That is, alpha I and beta I take values in 0 and 1. Right? So, and then we later show that the cost of this of a protocol solving this game. So optimal communication cost of a protocol solving this game is equal to optimal depth of a hazard-free formula computing here. Similarly, optimal size of a protocol solving this game is equal to optimal size of a hazard-free formula computing f. So the optimal size that we prove here 2 times 3 to the n minus 1, and this is given by this unfolding this recursive formula. As you see here that to get rid of one of the indices, you need depth 3. And as you unroll n times, the depth will become 3n. So really the optimal size protocol, the communication cost is 3n, or the depth of that formula is 3n. So then one can ask to optimize in terms of communication cost. And one can show that in fact there is a depth there is a 2n plus 1 depth hazard-free formula for multiplexer that you can obtain by giving a protocol of cost at most 2n plus 1. And the lower bound is log 3 times n that follows from the size here. So there is still a gap here. Similarly, for a hazard-free formula with alternation depth at most 2, we saw that the communication cost has to be equal to 2n plus 2. We further extend the hazard-free game to characterized limited hazard-freeness, which can lead towards general lower bound. So now let's have a preview of a quick overview of the lower bound result. And the lower bound says that the hazard-free formula size of the multiplexer is at least 2 times 3 to the n minus 1. For this purpose, we would need an auxiliary function. We call it a subcube intersection function. So this function takes 2 subcubes as input and is equal to 1 if the 2 subcubes intersect and is equal to 0 otherwise, right? And clearly the 2 strings you can interpret as subcubes, and that is what it does. It looks it is an indicator function of whether the 2 subcubes intersect or not. And the insight is that the hardness of solving Karchmer-Wigderson game for multiplexer, hazard-free Karchmer-Wigderson game for multiplexer, is captured by this subcube intersection problem, right? So we can show that the subcube intersection problem reduces to the hazard-free Karchmer-Wigderson game for multiplexer with 0 cost. So here, suppose Alice gets alpha, a subcube alpha, and Bob gets another subcube beta, right? So then Alice constructs alpha prime, 2 to the n length string over u and 1, and 1s are only at the positions that are given by subcube alpha. Similarly, Bob constructs beta prime over 0 and u. It is also a 2 to the n length string, and zeros are only at the positions that are given by subcube beta. Now clearly alpha, alpha prime together forms a minimal 1 certificate for multiplexer. Similarly, beta, beta prime forms a minimal 0 certificate for multiplexer. So the 2 parties can now solve Karchmer-Wigderson game over the multiplexer alpha, alpha prime and beta for multiplexer over alpha, alpha prime and beta, beta prime. And the answer to this game will help them deduce whether the 2 subcubes intersect or not. How? So one can observe that if the subcubes does intersect, that is subcube of alpha and subcube of beta have a non-trivial intersection, then the alpha and beta has to be consistent. And that means the difference has to be found in the data variables that is in alpha prime and beta prime. And if the subcubes are disjoint, that means they have to contradict on a single variable in alpha and beta, and so that the answer lies in the selector variables, that is alpha and beta. So from the answer to the Karchmer-Wigderson game for the multiplexer, they will be able to deduce the answer to the subcube intersection problem without any communication. So this shows that the size of the protocol solving Karchmer-Wigderson game for a multiplexer is at least the size of a protocol for subcube intersection. And it is well known that the size of a protocol is at least 2 times the rank of the communication matrix minus 1. So here, in essence, we have to show that the rank of the communication matrix for the subcube intersection function is full. That is, it is equal to 3 to the n, which is indeed what we saw, and it can be easily shown by induction on n. So for n equals 1, here is the matrix, the communication matrix, and it is easily seen to be of rank 3. And for arbitrary n, one can show that the communication matrix is basically a Kronecker product of this matrix times n. And since rank is multiplicative with respect to Kronecker product, we get that the rank of the communication matrix of the subcube intersection problem is 3 to the n, from where you get that the size of the protocol is at least 2 times 3 to the n minus 1. And in particular, size of the protocol solving hazard-free Karchmer-Wigderson game for multiplexer is at least 2 times 3 to the n minus 1. So let me now wrap up with open problems. One can ask, KRW conjecture in the hazard-free setting, is it true? Similarly, for the hazard-free formulas, we have an upper bound of 2 times 3 to the n minus 1 that follows from the construction of multiplexer. You just plug in the truth table of F, while the lower bound is 2 to the n over log n from the general formula. So there is a reasonable gap here to be closed. What is the truth value? Similarly, for the depth bound for multiplexer, we know that the n-bit multiplexer has a hazard-free formula of size of depth at most 2n plus 1, and this increase in size is only 1/8 additive increase, so it's not much. Whereas the lower bound from the size follows as 1.58 times n plus 1. So what is the truth value here? Similarly, one can try to prove lower bounds in limited hazard-free settings, progressing towards more general circuits. Similarly, one can also ask minimum circuit size problem for in the hazard-free setting. In particular, we know that minimizing DNFs is hard, is NP complete, whereas minimizing hazard-free DNFs is polynomial time solvable. So there is something to be explored here. Thank you for listening to me. And if you have any questions or comments, please feel free to write to us. Thank you.